Welcome to The Explainer, where we break down big ideas.
So what if the biggest truth in mathematics was only barely true? I mean, what if one of the most fundamental patterns in the entire universe of numbers, a pattern that mathematicians have been chasing for over 160 years, was only true by the skin of its teeth? Well, today we're going to unpack a brilliant proof that grapples with that exact mind-bending possibility.
All right, so our story begins with what's basically the Mount Everest of mathematics, the Riemann hypothesis.
Okay, so what is this thing? In a nutshell, the hypothesis makes this huge prediction about prime numbers, the building blocks of all other numbers. It says that these special points, called zeros, which seem to map out the chaos of the primes, aren't random at all. Nope. Instead, they all fall on a single, perfect, straight line. And this function you see here, this HO of z, well, that's the treasure map to finding that hidden order.
So, how do you even start to tackle a problem this massive? I mean, it's a beast. Well, back in the 1950s, a mathematician named Bruin had this brilliant idea. He thought, what if we could take this perfectly rigid problem and, well, what if we could just bend it a little bit to see what happens?
So he created this whole family of functions, and you can imagine it being controlled by a single dial. Let's call it t for time. Right? When that dial is at 0, boom, you've got the original Riemann problem. But as you start to turn the dial, the function itself changes, and those zeros, they start to move around. The paper actually has this beautiful way of describing it. It's like a backwards heat equation. So instead of heat spreading out and getting weaker, it's like it all rushes back together, concentrating into these super specific points. Kind of cool, right? And this whole idea brings us to the real hero of our story, the Bruin Newman constant, which we'll just call lambda. So what is lambda? It's the exact, precise tipping point on that t-dial. It's that one magic moment where the zeros, which might be scattered all over the place, suddenly just snap perfectly onto that single straight line. Now the implication here is huge. Think about it. If the Riemann hypothesis is true, it means the zeros are already on the line when the dial is at 0. And what does that mean for lambda? It means lambda has to be less than or equal to 0.
But then, things got really interesting. In 1976, this guy Charles Newman comes along and makes a totally different, really bold conjecture. He says the exact opposite. He says, no way, lambda can't be negative. It has to be greater than or equal to 0. Now wait a second, let's pause here. If the Riemann hypothesis means lambda is less than or equal to 0, and Newman says it's greater than or equal to 0, well, what's the only number that can be both? Exactly. And that's the big punchline we're building up to.
So now you've got this incredible setup, right? A huge, famous, unsolved problem is now tied to a single mysterious number. And that, my friends, launched a decades-long chase to pin down the true value of lambda.
For years and years, the main strategy was to find a floor for lambda. Basically, to prove it couldn't be lower than a certain number. Back in 1988, they proved it had to be bigger than -50. Okay, then computers got way more powerful. By 94, they'd pushed that floor all the way up to just a few millionths below 0. A few years later, it was billionths. And by 2011, we're talking about a number so ridiculously close to 0, it's hard to even imagine. They were squeezing lambda from below, getting closer and closer, but they just couldn't cross that finish line.
The ultimate goal, the holy grail, was to close that tiny, tiny gap. To prove, once and for all, that lambda just could not be a negative number. Period. And you know what? The breakthrough didn't come from an even bigger, faster computer. Nope. It came from a completely radical change in perspective, all thanks to two mathematicians, Brad Rogers and Terence Tao. Their big insight was to just step away from all the pure abstract math for a second. They started to imagine these zeros not as just dots on a graph, but as a system of actual interacting particles, and they say it right in their paper. They found that this physical analogy was the absolute key to cracking the whole thing open.
So picture this in your head. Each one of those zeros is like a tiny particle sitting on a line. And just like magnets, every single particle repels every other particle. They're all pushing each other away. And the math that describes how these little zero particles move when you turn that t-dial, well, that's exactly what physicists call backwards heat flow. Remember that? Instead of spreading out, everything concentrates. And that physical gut feeling, that was everything.
And this is where it gets really clever. This whole physical picture allowed them to set a brilliant logical trap using one of math's most powerful weapons, the proof by contradiction.
Okay, so here's how the trap works.
First, they assume the complete opposite of what they're trying to prove. They say, all right, for the sake of argument, let's just pretend lambda is a negative number. Now, if you assume that, it lets you mathematically run the clock forward. As time flows from that imaginary negative point up to zero, all that pushing and shoving between the zero particles forces them to settle down into a state of perfect, peaceful equilibrium. We're talking a perfectly even, spaced-out line, like an arithmetic progression. And that's where the trap springs.
Because this leads to a massive, direct contradiction. You see, on one hand, if their starting assumption is true, if lambda is negative, then the zeros at time zero have to be perfectly spaced out, like beads on a string, no exceptions. But, on the other hand, we already know for a fact, it's an established mathematical result, that the zeros of the actual Riemann function are fundamentally not perfectly spaced. They're all clumpy and irregular.
You just can't have it both ways. The system can't be perfectly regular and totally irregular at the exact same time. It's impossible. So the only logical way out of this paradox is to realize that our initial assumption, the one that started this whole mess, has to be wrong. Therefore, lambda cannot be negative. QED.
And just like that, this incredibly elegant proof finally establishes Newman's conjecture. Lambda is greater than or equal to 0. But wait, the story doesn't end there, because this has an absolutely stunning implication for the Riemann hypothesis itself.
Okay, so let's put the two big pieces of the puzzle together. Remember, the Riemann hypothesis is true if lambda is less than or equal to 0. And now we know for a fact, thanks to Rogers and Tau, that lambda must be greater than or equal to 0. So, what's the only number in the entire universe that fits both of those rules? That's right, it's 0. Lambda has to be exactly 0. And what that means is that the perfect, beautiful order predicted by the Riemann hypothesis, it isn't some rock-solid, unshakable truth. It only just barely manages to be true.
And that brings us full circle, right back to Charles Newman's original, shockingly insightful words. Now, this proof doesn't solve the Riemann hypothesis. Not yet. But it paints such a fascinating picture. It suggests that if the hypothesis is true, it's only barely so. That beautiful, perfect order in the prime numbers, it might exist, but it's hanging on by a thread. It paints a picture of a universe of numbers that has structure, that has a pattern, but maybe only by the absolute slimmest, most delicate of margins. A constant that's just barely true.